What's up guys, welcome back to another video. My name is AzimuthAngle and today I'm going to be giving you a short course introduction. It's going to be on solar energy system design, and I thought, you know what, let me just refresh and give you guys a small course outline covering these small basic step-by-step process on what you need to really give a ground up strong foundation, so you can have an idea of what solar energy is about, some key topics, some formulas, some theoretical background knowledge. And this will be divided into 4 parts or 4 weeks. So as you can see, the course outline from week 1 to week 4. So the first week, which is going to be today's video, I'm going to be talking about the energy from the sun, the relationship between the sun and the earth, how it varies, the sunlight that varies across the earth's surfaces, and how we can use that sunlight energy to find online resources and data to then build a solar system. And then from then on, in weeks 2 and 3, we're going to be looking at the circuitry basics, the common basic knowledge of the solar panels itself, the characteristics of the IV curve, the current and voltage, the power specifications of PV modules and arrays specifically, and designing them. On week 3, we're going to size these PV systems, get the power output, the PV output, and based on that, it changes based on the temperature, the cold weather temperature conditions, the VOC, the warm temperature conditions as well. The voltage fluctuates in the warm conditions as well, and we're going to be taking into account the shading losses that can be present throughout the year. So how much available solar sunlight will be there, taking into account of shading losses. And then the final week is going to be a package combining all the previous weeks with the practical and the theoretical knowledge, to have the site surveys, to design the system, solar system, make sure you're able to size your solar system, choose the correct modules, inverter, and to have a full-on analysis report, simulation, all these sort of background checks for the complete overview of solar. So without further ado, let's get into the video with week 1. So week 1 is going to be the energy from the sun. So for energy from the sun, there's different types of radiation that is available on the spectrum. As you can see, there is X-ray, there is UV, ultraviolet light, there is visible light, there is infrared, then there is radio. And based on the fluctuation of these wavelength, the X-ray wavelength is shorter in length as compared to the radio. Radio is longer in wavelength. And we know from the formula on the left hand side, you can see the equation energy equals hc over lambda. H is the Planck's constant value, multiplied with c, the speed of light, divided by the wavelength. In a more broad view, for the radiation on the Earth's surfaces, we can look at on the y-axis the irradiance, which is the sun's intensity in watts per meter squared. And on the x-axis, the wavelength, as how the wavelength, as it gets shorter, the energy is higher, and as the wavelengths get longer and longer, the energy decreases. Ignore the H2O and O2, and then CO2. Just ignore that. Just look at the yellow light and the red light. The yellow light is the sunlight that is reaching this earth without the atmospheric pressure of the absorption. So it's basically the sun, the energy of that sun in space. So it's going to be very hot. There's no atmospheric pressure to prevent that reduction of energy, and that's why the yellow light is the full sunlight exposure. If there was no atmosphere, it was exposed to in space, and if we were to receive that sunlight energy, we would be burnt alive. So this is why the red light is when the sun's energy being passed through the atmosphere of the earth and then reaches the earth's surfaces. That is what we receive, much lower of course. And the visible spectrum is between 400 to 700. So that is when the solar panels are normally operating at that range of wavelength from 400 to 700 nanometers. So this is overall just a general introduction, background check of the sun's energy radiation in regards to the earth. without the atmosphere and with the atmosphere. Take into consideration. The key points that you also need to take into account is like I mentioned before, energy is inversely proportional to the wavelength. Solar irradiance, as I mentioned, is power divided by the area, and it measures the brightness and intensity as that changes based on the distance between the sun's and the Earth's atmosphere, the sun's surfaces. So if there's a shorter distance between the sun and the Earth's surface, then there's going to be high intensity. If there's a greater distance between the sun and the Earth's surface, it's going to be lower intensity, lower solar radiance per meter squared, or the watts per meter squared, right? And taking into account of the solar declination is basically the angle that the sun is facing towards the equatorial plane of the Earth throughout the year. When the Earth is rotated around the sun, the angle of that changes throughout the year, and I'll get more into that later on. I'll show you a picture of that, and you'll get into a more understanding of what I mean by the solar declination angle. The azimuth angle, as we know in today's solar energy terms, it's the angle that is oriented due north of the compass. So we know that at north it's 0 degrees, that's the standard process. East is 90 degrees, south is 180 degrees, west is 270 degrees. Azimuth angle normally is, when you apply, is how the solar panels are going to be oriented and is going to be positioned based on the location that you're living in. So for example, if I am living in a northern hemisphere, so in the northern hemisphere, always you're going to be positioning your solar panels due south, so facing towards south with an azimuth angle of 180 degrees. And if I'm living in the southern hemisphere, it's going to be the opposite, of course, where the solar panels are going to be positioned due north, facing with the azimuth angle of 0 degrees. And based on that, then you have to take into account the elevation angle or the tilt angle. So that is how high the solar panel is going to be positioned from the ground. So it's the angle of the sun above the horizon. And normally the rule of thumb is that the latitude of the location of the Earth's surface is the latitude of that. If you're, let's say it's 45 degrees in the northern hemisphere, then the solar panel's tilt angle or elevation angle is going to be 45 degrees. So it's going to be matching with that of the latitude of the location that you're based on the Earth. All right, that's how it is. Zenith angle. So zenith angle is just basically the complement of the elevation angle. It's the angle between the sun and the 90 degrees or perpendicular to the Earth's surfaces. So if the solar panel is like this, directly 90 degrees to the surface, that's the zenith angle. All right. Now the solar declination, as I mentioned early on, in the summer solstice, so basically the summer season in the northern hemisphere, or the winter solstice, winter season in the southern hemisphere, the declination angle is at its maximum at 23.45 degrees. So this is how the sun or the Earth's position is, the angle during the summer solstice in the northern hemisphere, or the winter season in the southern hemisphere. And in the spring season in the northern hemisphere, or the autumn season in the southern hemisphere, the declination angle is going to be 0 degrees. So it's going to be the same position. The Earth's angle is not going to be tilted towards or away from the sun. It's going to be the same, with the equatorial plane of 0 degrees facing the Earth, facing the sun. So the winter season in the northern hemisphere and the summer season in the southern hemisphere, that's when the declination angle is going to be minus 23.45 degrees. Let's get more into the application, applying that knowledge to the solar panels. So as we know, the sun is pointed towards the solar PV panel. Let's focus on the azimuth angle first. Azimuth angle, as I mentioned, it's the angle that is starting oriented due north from the compass. So north is 0 degrees, east is 90 degrees, south is 180 degrees, west is 270 degrees. And based on the location, the solar panel is either going to be going facing due north, due south, due east, due west, based on your location. So in the northern hemisphere, you're going to be facing due south. In the southern hemisphere, you're going to be facing due north. Simple as that. Now, whether it's landscape or portrait, the solar panels, that is up to you. Most residential PV rooftops, they go for a portrait configuration. portrait layout, just more aesthetic, more easier, accommodate the space of the rooftops, where you can fit in more solar panels. And on ground mounted or commercial rooftops, the preference is towards landscape, where you're able to cover large area of ground, and then of course the shading that is going to be passed behind the solar panels to cover into that, and then you have to size and take into account the space consideration, so how much space, the gap it needs to be from between the rows and beside each solar panels. But that's a different story. But overall, so the azimuth angle I mentioned, how we need to position based on the location, and then the tilt angle, or the elevation angle from the sun above the horizon of the earth's surfaces, that depends on the location that you're living in, latitude. So you have to match that with the latitude, not the longitude. The longitude is just the horizontal angle. Latitude is more the vertical angle, which is what we need in comparison to the sun's angle that is positioning or moving throughout the day. And from there, we can then move on to the types of sunlight that is varied across the earth. Normally there are 3 types of sunlight variation. There's the one that is absorbed. Sunlight can be absorbed by the clouds or the atmosphere. It can be scattered. So scattered meaning it is reflected, or is scattered, hitting the clouds in the atmosphere, and then it's scattered away. Or it is reflected, so it's reflected off of the atmosphere or the clouds and then towards the earth's surfaces. So these are the 3 types, and from there, if we want to look at the more detailed, diffuse radiation, so it is a light when it gets scattered and indirectly reaches the ground. So diffuse meaning that if the sunlight from the sun hits the cloud and then it reflects and then it hits the ground, this is diffuse radiation. Direct radiation, it is when the light reaches directly to the ground, to the surface, without being reflected off of the atmosphere or the clouds. And then of course there's absorption, which is when if there's sunlight that is radiated off the energy from the earth's surfaces, that can be absorbed by the clouds and the atmosphere respectively. So from this we can then know the total global radiation. The total global radiation is a combination of both diffuse and direct. So when you add them both together, then you'll be able to have a better understanding of the global radiation, the data of that particular specific location that you can find online, which I will mention in the later section, in the next slide. Then there is the air mass, which is also very crucial to know. The air mass is basically the air thickness, or the gap that is placed whenever the sunlight is passing through the atmosphere. So the air mass, the air thickness, normally that intensity decreases whenever the light passes through the atmosphere. And for a standard testing condition, the STC, the default value for the air mass is 1.5. But to calculate that air mass specifically is basically you divide 1 over the sine of the elevation angle. So if I have an elevation angle of latitude, let's say 45 degrees, I do 1 divided by sine 45, and that will give me the air mass value. So it'll give me how much air thickness the sunlight will be going through when it passes through the earth's surfaces. Okay, so that's just a general idea that you can know as a bonus. So this is a key figure, just to demonstrate what I mentioned in the previous slide, where the sunlight is either diffused from the atmosphere, from the clouds or the atmosphere, and then towards the ground. Then there is direct beam that's hitting the solar panels, or from the ground reflected to the solar panels, and then either can be absorbed from the atmosphere or the clouds, or scattered, so atmosphere scattering, or diffused. So yeah, this is the typical the arrow representation of the process, how the sunlight is being passed through different stages of processes of the earth and to the panels, of course. Another key point is that at standard testing conditions, the solar panels, solar radiation is basically at 1000 watts per meter squared. That's the default value at full sun hours. All right, so this is how much solar panels are going to be receiving at full sun hours, STC 1000 watts per meter squared. And if you want to know if your place is receiving, let's say, 6 hours with a solar radiation of 700 watts per meter squared, then that means you're going to be having 4200 watt hours per meter squared. And if you divide that value with 1000 watts per meter squared, the STC value, then that means you're going to be receiving 4.2 full sun hours of maximum full sun hours. Okay, it's just a common example, just to have an idea of what I meant by that solar radiation. And then we know that energy is power times time, because the sunlight energy, if we divide that by how many hours in a day you have sunlight, based on the location, the in northern hemisphere or southern hemisphere, or the seasonal change, whether it's summer, winter, autumn, or spring, based on that, energy divided by time will give you the power of sunlight per meter squared of the area that's going to be reaching the surface and received by the sunlight of the solar panels, right? Per area meter of the sunlight's area per meter squared. And from that, the solar insolation, or the solar insolation, is basically the incident solar radiation, which is the quantity of sunlight energy that reaches the surfaces. And based on that data, to find that, you can use the NSRDB or the PV watts. NSRDB is the National Solar Radiation Database, which is a well-known historical database that has record temperatures of or data sets of for the past 3 decades, and you can able to find various data sets on your location, but it's mainly focused in the US regions and states. PV watts is global, so you can look at. So PV watts is a global online resource tool that you can enter your zip code, your location, whatever it is, address, into the search bar, and then you're able to find the solar insolation data per month and the yearly annual value. And then using the data, you can also be getting the total global horizontal irradiance, which is the combination of both diffused sunlight and direct sunlight irradiation. So it gives you more precise, accurate data. And like I mentioned, PV watts, so as you can see, you can enter your business or home address, zip code, whatever, and once you enter that, you can then get the results, the solar radiation on the right hand side the table, which just shows you kilowatt hours per meter squared. So you can get a monthly value, and you can divide that monthly value on how many days there are in a month to get the daily value as well. And that adds up to the estimation of the annual solar radiation as well. And these values that you can use to then size your solar energy, solar PV system, which, as you can see, these are the important formulas and key formulas that you need to know to be able to calculate in the next week's lectures, weeks 2 and 3. They're going to be used to size your solar PV system. So if you look at it, pause this video, take a screenshot, write this down. This is important. You need to know about this. So the annual insolation, to find the yearly annual insolation or the solar radiation, you simply multiply the average daily insolation that you would receive in a day with how many days there are in a year. So for example, if let's say January has 1.52 monthly solar radiation, if I divide the January with, let's say 31 days, I'll have the daily average solar radiation, and then I multiply it with 365 days, I'll get the annual solar radiation. Already PV watts did it for us, but you can do it by yourself to match that with the PV watts calculation. And then from then on, you can find the PV energy production, so how much energy is being produced by the solar PV system. So that formula is equal to the solar system size. So if you have a 5 kilowatt solar system DC, 8 kilowatts, 10 kilowatts, 15 kilowatts solar system size, you can multiply that with the solar system efficiency. Normally that average value of efficiency is 80 to 85%, And, there's other factors that need to take into account, which is the the mismatch losses, the wiring losses, the inverter losses, the module degradation losses, all that sort of stuff. You can maybe take 75% efficiency for more accurate data, but to be on the safe side, rule of thumb, take 80 to 85% of the system efficiency and multiply that with the annual solar radiation that we found, or that you can use in the previous formula, and then that gives you the PV energy production. If you want to go the other way around, you can mess around with the formula, rephrase it, and you can divide the PV energy production with the system efficiency multiplied with the annual insolation solar radiation to get the solar system size PV watt in kilowatts, so you can determine how many solar system you would be having if you have this PV energy production in a household yearly. So then you can get the right solar system size. And overall, that is it from me. Yeah, this is the week 1, end of week 1. I hope you guys enjoyed it. In weeks 2 and 3, I'll be talking about. Weeks 2 will be more theoretical. Week 3 will be more practical, applying the knowledge from week 2 and week 1, and then getting a more calculated analysis. So that's all for today. I hope you guys enjoy the video. Please make sure to like, comment, subscribe. If there's anything else, let me know in the comments down below how you thought about this course. If there's any questions you need to ask, let me know in the comments down below.